Okay, maybe I'm actually recording this time. Right, so this is demos of a potential online course for Math 211, which I'm now in the second semester of teaching it live. So I'm using it as my guinea pig to try to put a week of it online. So at this point in the semester, they would have just gotten back exam 2, and I already have online all the reviews for exam 2. And so I'm trying to convert some of the lectures to an online format. See how that works. Okay, so we have in chapter 4.1 through 4.3 of our textbook, we're going to be talking about maxima, minima, and points of inflection. And calculus texts go through this routine. They start with a function. It's usually a polynomial. Then you find the first and second derivatives, and you set those equal to 0, find where it's increasing, decreasing, concave up, concave down, and you know what all that means now because you've done that already. But now what we do is we try to actually plot accurate polynomials using what we know about calculus. So we try to put our graphical skills and our calculus skills together. However, before we start in on this, I'm going to talk about polynomial behaviors because knowing is half the battle. Okay, so what I'm going to actually kind of call this is a polynomial review. It's in quotes because for some of you it may be new information. But the more you know about polynomials, the better you're going to be able to plot them in calculus. As you try to build up your knowledge, you don't want to just build one block on top of the other so you have a big obelisk in the sky. You want to build out a broad base so you can support the new knowledge that you're gaining. So what I'm trying to do here is broaden your understanding of basic polynomial understanding so that you can then graph them better when you're graphing them with calculus. Okay? So a polynomial has roots and one more piece of information, and this is what I want you to think about polynomials. And why am I saying this? Because in high school, what you're probably taught is to look at a polynomial this way. So I'm going to just make up a polynomial, okay? 4x cubed plus 7x squared minus x plus 1. Okay, so that would be a cubic. This is a cubic, and what you see is coefficients. You see a list of coefficients 4, 7, minus 1, 1. You're just looking at, for example, you look at this guy, and that's a coefficient. This guy, 7, is a coefficient. The negative sign is really a negative 1. And then the plus 1, those are your 4 coefficients. Okay, so that's what we look at in high school. And there's nothing wrong with that, but that gives kind of a faulty view of what polynomials are doing in their hearts. You know, like what it is that's driving these polynomials, and how polynomials are used in engineering and design. I want you to rethink how you see a polynomial. I want you to think of every polynomial as being something that just has yet to be factored. So I'm going to make up a different order 3 polynomial, so it's not the same one, but I'm going to do something like this. And if I do something like this, I can very, very easily plot this. Okay, so this has 3 roots, and these are important. These tell us everything we need to know about the behavior of the function, and this just stretches the function, and that is less important as far as graphing, in a sense that you need to know that number in order to tell exactly how high the function goes. But if I want to plot this guy, all I have to do is say, okay, here's my x-axis, and I'm not even going to worry about this stretch factor over here. This guy, I'm going to completely ignore him. Didn't mean to turn that color. Okay, so I'm going to forget about that guy, and so I don't need a y-axis at all. But I know there's a root at x equals 1, there's a root at x equals negative 2, and there's a root at x equals 7, and I'm just going to weave in and out of these roots. So I'm going to start this function. You see this stretch factor is positive, so I'm going to start in the upper right because it means that eventually this thing is going to go positive. So eventually it's going to go positive, so I just draw my curve backwards, starting from quadrant 1. If there had been a negative sign here, I would have started in quadrant 4 and then wiggled through the other way. That's it. So if you have a polynomial that's already factored, Graphing it is really, really easy. And that's the part I want you to understand. Now, if your polynomial has repeated roots, let's still keep looking at other possible behaviors. Okay, you could have, if you have a cubic, for example, you can have this kind of behavior. You could have one real root. Again, this is a cubic. And the fact is, I could have actually moved this around, and so I would have 3 real roots, but just by changing that constant, this little constant on the end, this little guy, why do I keep doing that? This little guy, when you tweak him, that changes how many real or imaginary roots you have. So the fact is that since we bend around like this bend is telling us we have 2 more roots, and it's a complex pair. And we know it's a complex pair because it doesn't go through the axis, but we know that they're actually roots because the thing bends. Okay? So I know this is all new to some of you, and I'm just going to repeat this more slowly as I go through the various examples. Okay, so examples. Alright, let's start with something we all know how to do. Y equals x minus 3. I know you guys know how to do that. Okay, so I can just look at this rather than doing the line like what's the y-intercept, what's the slope, and all this stuff. I don't care. What I'm going to do is I'm going to just see that the root, or the 0, is at x equals 3. What do I have to make x be so y equals 0? Okay? And that's going to be positive 3 causes this thing to be 0. And again, there's no negative coefficient here as the leading term, so I'm just going to dive down this way. That's it. No problem. That's how I plot that line. And yeah, okay, it has a slope of 1, but I don't actually care about that at this point. Okay. Here's another example. What if we put another root in this? Alright. Now I have a positive 3 and a negative 3 for roots. And I'm going to just, again, there's no negative coefficient over here. So I'm going to start in quadrant 1, way up here, and I'm going to just dive through and dive through. Now, the roots are symmetric, so the picture I'm drawing should be symmetric. Well, what about if I do something like this? X minus 4, x minus 1, x plus 1. Easy peasy. All I do is I say, well, if I make x equal 4 here, x equal 1, x equals 0, or x equal negative 1, that gives us the various roots. Okay, and again, there's no reason to start in quadrant 4. There's no coefficient out here that's going to cause us problems. And so we start in quadrant 1 and we dive down, up through, and that's all you do. Pretty easy, right? And you think, oh, I wish polynomials were always that easy. Well, they actually are. Right, so let's do another one. Okay, so we have, I don't even need the y-axis, but if it makes you happy, you could put it there. X equals 1, x equals 0, x equals negative 3, and x equals negative 4. And then I say, oh, no negative coefficient over here, so I just go b, b, d. That's it. Done. Now, what if I do have a negative? Or what if I have 2 roots together? Well, let me pause this discussion for a second to say, well, what happens at y equals x squared? You all know what happens at y equals x squared. That happens to be 2 roots together at the origin. So the way I'm going to draw this is I'm going to put, when I draw on my axis, I'm going to put a point to mean I have a root, but a bullseye to mean I have a double root. And when I hit a double root, that means I have to turn around. I have to hit the axis, but I can't pass through. It's going to look exactly like what happens at y equals x squared. Okay, so let's go ahead and we're going to add these two concepts together. I'm going to actually put a leading negative sign, so I'm going to start in quadrant 4 this time. But I'm also going to have some double roots and see what happens. Okay, it's still going to be easy. Watch. Okay. Axis if you want it. Alright, so at x equals 3, right about here, I'm going to have a double root. At x equals 1, I'm going to have a single root. And at the origin, I'm going to have a double root. And then at x equals negative 1, I have a single root. Alright, and now I'm not starting up here because there's this leading coefficient of negative 1. So I'm going to start down here, and I'm going to go and hit this bullseye but turn around. But I do have to dive through. So I dive through at 1, and then I have to do this little turnaround here and down. And you may say, well, how do I know how tall to make these? How do I know not to make this really, really high? Well, you do what actually comes natural. What you want to do is pretend like you have a thin piece of plastic that's very pliable, and then you just go ahead and use that thin piece of plastic in your mind and bend it, and that will, it'll just work out. Okay, think one more example, and then I'm going to have to see you on the next video, okay? Which for me will be longer than perhaps it will be for you, because my alarm just rang and I have to go see my live students in my class. Wow, everything's yelling at me. Okay. Alright, x equals 1, and it's a bullseye. X equals 0. X equals negative 2. I actually had my students in my live class tell me where to put the dots in the bullseyes, so I'm sure you could just finish this yourself. Okay, now do we start in quadrant 1 or quadrant 2? And you should tell me we start up here in quadrant 1. Okay, and then I'm going to just come down, turn around, pop through, and then turn around and pop through. Alright, and okay, well, I guess I will see you on the next video.